So we're gonna end the section with a problem, uh, which contains all the elements of the technique of linear approximation, and also asks us to incorporate the estimation of the error introduced in the previous video. So the problem says estimate the arctan of 1.01 and estimate the error. Okay, so for the solution, we're going to be very detailed. Um, Start by identifying things. So the first thing is we need to identify, so the first step we need to identify f of x, so the function we want to linearize, the point x naught, and finally the new point x, the point at which we wish to approximate f. Right? Because I mean sometimes problems will be worded in this way, so just given a function at some point and then estimate the error. As I said before, if you just look at the problem and you see there's an arctan, then that's probably the function f, and that's the case. So f of x is arctan of x. Now, at what point near 1.01 do you know arctan? At 1. That's the that's a point where you know arctan. So here we're considering the branch for which arctan of 1 is equal to pi over 4. Remember the sign, we already used that in the previous problems, where we computed sine of pi over 4, which was equal to square root of 2 over 2, and cosine of pi over 4, which is also square root of 2 over 2. So the tan of that of pi over 4 is 1. So if x is equal to arctan, and then what is the point? X naught, as we said, is going to be 1, because we can compute here. At that point, we can find the arctan, the main branch of arctan. So what is the point x? X is 1.01. So these are the three things we need to identify from the problem. Okay, so now that we've done that, the second step is to record the values of x, f of x naught. And what else do we need for the linear approximation? We need the value of f prime. We already said the arctan of 1 is equal to pi over 4. Now, what is the derivative of arctan? It's 1 over 1 plus x squared. Remember we computed that in the section for implicit differentiation, and where we computed the derivatives of inverse functions as an application of the chain rule. Okay. So then this implies here that arctan prime at 1 is 1 over 1 plus 1 squared, which is 1 over 2. So we have the value of arctan and arctan prime at 1. That's what we need. Then, third step, Third, step, what is L of x? L of x is f of x naught plus f prime of x naught times x minus x naught, which would be, in this case, arctan f1 plus arctan prime f1 times 1.01 minus 1. This is just 0.01. And this is just equal to pi over 4 plus 1 over 2 times 0.01. I mean, this is L of x, so L of 1.01 is equal to that, right? So our approximation in the end is this. And what is the to estimate the error? We need to bound f double prime now. The absolute value of double prime at least between 1 and 1.01. So what is f double prime of x? Is 1 over 1 plus x squared prime, which is, according to the chain rule, 1 plus x squared squared times the derivative of what's inside, which is 2x. So now f double prime of x is equal to 2 times the absolute value of x divided by 1 plus x squared squared. Why? Because the absolute value of a squared is just itself, because it's a positive number. Okay, so how do we, so we need to maximize this expression. Or in fact, we just need to bound this expression. So that's a better wording. So we need, because we're not going to find the maximum yet. This is something we're going to learn to do in the next section. But we can speak about bounding it, finding a bound to bound this expression from above. And for values from above, at least for values between what, according to the previous video, 1 and 1.01. So here's a question. How do we make the numerator here as big as possible? By picking the largest value of the two. So we can bound for any x in between 1 and 1.01. X, the absolute value of x is going to be less than 1.01. So you have to pick the biggest possible number. Now for the bottom, so for the denominator, when is that? So if we want to maximize we want to bound this expression from above, we want to make the denominator as small as possible, and that happens when x is equal to 1, right? Because the smaller the denominator, the bigger the quantity here. So 1 plus 1, that happens when x is equal to 1, so 1 plus 1 squared. This is equal to 2 times 1.01 divided by 2 squared, which is 4. And this is just equal to 1/2 times 1.01. You see, actually, I chose this example because it's a little bit more complicated than you'll normally see, but it's not something that you'll definitely not see. So something like this can happen, or at least some parts of this problem could be in your exam. At least the first one. So estimate R10. So estimate a function at a weird point, and you need to identify the function, the points involved, x0 and x. Estimating the error is something that used to be more of a standard question in the exam. Not so much anymore, but since it could be there in some form or another, yeah. I mean, I'm just giving you an example, the most complicated thing that you can possibly see in the exam. But okay, so this is a bound for the error. In the end, remember the error can be at most k over 2 times x minus x naught squared, which in this case happens to be less than or equal to separated. What is the bound we found for k? 1/2 times 1.01. Remember, this expression here in circle comes from the second derivative. So we're bounding the second derivative by, or k, when the k, the second derivative, by 1/2 times 1.01 and times x minus x naught squared. What is that? It's 0.01 squared. Okay. 1.01 minus 1 is 0.01. So this is x minus x naught, which you're supposed to square, and you have the bound for k, which is this, and this is the formula that bounds the error. Okay, so next video will be a review for your second midterm. I hope that's enough, for now. Then we'll continue, we'll move on to the final part of the course.